Today, Jie Shen from the University of Purdue. He's in the math department there and also the director of what is equivalent to our CAM, Computational Applied Math Center. He won a Fulbright Award in 2008 and he's a fellow of the AMS. He is known, I like to describe him as one of the great thinkers in spectral methods and computational fluid dynamics. So I hope today he's going to share some wise words with us on structure preserving numerical schemes.
Okay, thank you, Alex, for the invitation and for the nice words. So I'm going to talk about today, not much about spectral methods, but about some recent work we did for complex dissipative conservation in nonlinear systems. So this is a joint work with a couple of my former postdocs and former students. So here's a brief outline. So I'll start with some motivation, and then I will give a brief review about how to construct energy stable schemes for gradient flows. And here is the essential part, which is probably 3 or 4 slides. So I will explain this. Everybody can understand this. It's very simple and easy to understand. So the key part is here. And once I get through the algorithm, and I will present a lot of different applications, because this method is quite general. You can apply to a large class of problems. I just pick a few that which are typical, and conclude with a few remarks. So we know that the physical systems. So where do all those equations come from? They either come from conservation laws, mass conservation, momentum conservation, and energy conservation, and so forth. Or they are cooked up by physicists, starting from some free energies or Hamiltonians, and then you let the free energy evolve. You get you start with a free energy or Hamiltonian, and then the equation, most of the equation from physics come from this kind of form. So you take the phi is unknown. You take the time derivative, it equals to the variational derivative of this free energy, and you have it's sort of a gradient descent, right? And the G, if you think of a positive definite operator, then this gives you a gradient flow. What is gradient flow? It's just the energy will decay with time. Or if you take G, this operator, to be skew symmetric, then the energy will conserve. The energy will stay the same. So you get a sort of a conserved system or Hamiltonian system, depending on how you see it. So the important property is if you take the inner product of this equation with the variational derivative, and you see that on the left-hand side, you get the time derivative of the free energy. And on the right-hand side, as I said, if this is a positive definite, it's a dissipative. If this is skew symmetric, this one goes to 0, it's conservative. So this is the important property associated with this system, right? And so there are so many equations which can be written in this system. You have the easy example, Alan-Carr equation, Carr-Hillier equation. The more complex example, phase field models, or you have L1 minimization, image processing, optimal transport, or those are dissipative systems. For now, for conservative system, you have nonlinear Schrödinger equations, Bose-Einstein condensate, Sine-Gordon equations, etc., etc. Right? Many systems can be written in this form. And so the talk is about how to construct simple and accurate numerical scheme which can preserve this structure, preserve the energy dissipation or energy conservative structure. You would like your numerical scheme to preserve as much structure of the PDE as possible, right? That's the goal. And oftentimes, if you cannot be the scheme is not dissipative or conservative, you get non-physical results. So that's the goal. Okay, now let's give you some examples for gradient flow examples. For example, you can take this operator G to be the identity, and then this is called the gradient flow in the L2 sense. If you take the G to be minus Laplacian, you get this is called the gradient flow in H minus 1, in H minus 1 norm. Or you can even take this G to be minus Laplacian to some fractional power. Then you get H minus S fractional gradient flows. And so what is a typical free energy? A typical free energy takes this kind of form. So this is a very common free energy. You have a bulk part, half of gradient phi to the square, and you have a nonlinear potential. Which can take many different forms. Most common is the double well or the log form, right? So in this case, then the L2 gradient flow, you get the famous Alan-Carr equation, and you take the H minus 1 flow, you get the famous Cahillane equation. So those equations are very typical in material science and fluid dynamics. So I'm going to talk about time discretization. So there's a long history of constructing try to construct efficient schemes for this type of energy, dissipative system, or more precisely, gradient flow. So it started, I guess, maybe with a fully implicit scheme. So the way to construct a numerical scheme which follows, mimics the behavior of the PDE is the easiest way is to start with the implicit scheme, fully implicit. Then you can pretty much preserve the structure quite easily, and you can do that. The first such a nice scheme is constructed by Du and Nicolais in the early 90s. So they can be actually unconditionally energy stable, but since it's a fully implicit, you have to solve nonlinear equation at each step. And you don't even know whether the nonlinear equation will have a unique solution. Right? Nonlinear equation may have multiple solutions, and to get a unique solution, you may need your time step to be very small to get the solution to be unique. So that's the fully implicit scheme. And then people try to use to do some sort of linearly implicit scheme. You treat the high derivative part with implicitly, and treat the low or the nonlinear part explicitly. So you get a simple scheme. Right? This way, you don't have to solve nonlinear equation at each time step. But the problem is you lose the unconditional stability. Your stability is related to the type of nonlinear terms you have. And then people can start to add some stabilization term, extra dissipative term to this. Yes?
What is your precise definition of energy stable?
Energy stable means my discrete energy decays at each time step. So just like the continuous case. That's good. I should have explained this. And then people start to add a stabilization term to it, so that you can make some cases the scheme to be unconditionally stable, but with some conditions. And usually you can only end up with first order schemes to be unconditionally stable. Second order scheme, it becomes extremely hard to do it. So this type of scheme has been very popular. It's very efficient, but it's difficult to get to high order stability. Then there's a class of method called convex splitting. Okay, this has been extremely popular, and it started with maybe even earlier. So the convex splitting idea is very simple. You have your nonlinear potential, you split them into the difference of two convex functions. Suppose you can do that. then you treat the positive convex function implicitly. The negative convex function is concave, so you treat it explicitly because that will not give you anything. So for that, you always end up with unconditional energy stable scheme, no matter what. So if you can, if you can split your energy like that. And but the thing is, first order scheme are fine, but it's difficult to get a second. For very simple case, there are some second order scheme, but in general, you don't get a second. But and still, you need to solve a nonlinear equation. But this nonlinear equation is much better than here. You have unique solvability, so you know the solution will exist uniquely for any delta t. So this is much better. And so this scheme has been very, very important because it's quite general and sort of easy to solve. Then, about 2 or 3 years ago, there's a new type of a method called the energy quadratization method developed by my former PhD student, who's now professor at South Carolina University, and his colleagues. And this is a very, very it's sort of a revolutionary idea. They introduce some extra variables, and once you have these extra variables, they write every nonlinear term in the quadratic form, and then you can come up with a scheme which is always linear, which you can always do second order, no problem, even higher order. And they are also unconditional energy stable. So you have many good traits, many good properties, and work with a large class of gradient flow. So the only problem with this type of scheme is at each time step, or if you suppose you have you have your own variable, you have the coupled, you have extra variable, they are all coupled together, and you have to solve coupled non-constant coefficient problem. Each time is different. Each time step is different. So this becomes quite costly if too much in time. But otherwise it's very nice. You have all those good properties. Only it's you have to solve coupled system with non-constant coefficient. It's not constant, non-constant. Okay. So pay attention to the next few slides. It's what I'm going to represent. So this method we call the scalar auxiliary variable approach. So this is inspired by the previous energy quantization method, but it preserves the advantage and overcome many of the shortcomings. So how does it work? I am going to assume my free energy can be split up into 2 terms like this. This is arbitrary. Any free energy, you split you take out the linear term, you put everything else into this part we call the F phi. Okay, this is very general. There's not much assumption here. And the assumption is that this part, the integral of this part should be bounded from below. And this is physical because you don't want to minimize something which is unbounded from below. And then, once you have this condition, you introduce one scalar auxiliary variable we call it SAV. So it's just the square root of this E1 phi plus this constant C0, so that this is well defined. And you see that the space variable x is integrated out. So it's only a function of t. It's a scalar function of t. Okay, by introducing this, I'm going to rewrite my original system. This is my original system, right? I'm going to rewrite my original system into a new system. So how do I rewrite this? Okay, so d by dt equals minus g, and I'm going to denote this thing by a new variable mu, and this is mu in material science called chemical potential. So what is mu? Mu, because E is here, you take the variational derivative. For the first term, you get F phi. For the second term, you get f prime of phi. But I'm going to stick in front of f prime phi this term here, which is the constant 1, RT divided by itself, right? Which is 1. So I do not change my equation. And then, since I have an extra variable r, I need an equation for r. So I take the time derivative. I get this equation for r. And this is a equivalent system to this one. So at the PD level, they're exactly the same. Nothing changes, right? But at the discrete level, you have much more flexibility now, because here it's just you are dealing with phi, and now you see you have phi, mu, and r. I can do some of them implicitly. I can do some others explicitly. I have much more flexibility. So this is sort of a relaxed system. So my guiding principle in designing numerical scheme now will be, I will treat all the linear terms, dissipative systems, implicitly. So this is a positive definite operator in general. And this is also a positive definite or conservative. I treat those things implicitly. And the nonlinear terms, no matter how complicated they are, I treat them totally explicitly. And this R, it's linear by itself, so I'm going to treat it implicitly. So this is my guiding principle. And then I can choose my order. I can do first order, second order, third order, fourth order, whatever. Right? I give an example of a second order scheme with PDF. So this is a second order approximation to the time derivative. And so here the nonlinear terms are treated explicitly by extrapolation. Second order extrapolation. Nonlinear term, I don't care what is the form. I just do it explicitly. And here's the implicit. And the second order derivative, second order approximation of the derivative. And here's the nonlinear term. So that's a scheme. That's a scheme. Obviously, it's a second order accurate. Right? You can do third order, first order, whatever you want, you can do that. Using the same principle. But what is the property? What is the property? The first thing is, if you take the inner product of this equation with mu n plus 1, you see, you get the dissipative term here. You take the inner product of the second equation with this second order approximation of the derivative, and this with this, you also get the dissipative term. And the third equation, you multiply by 2 times Rn plus 1. And why do I want to multiply 2 times Rn plus 1? Because I have here Rn plus 1. And here, if I multiply by Rn plus 1, it's exactly the same of this one, inner product with this. So when I add the two results together, the nonlinear term cancels out. No matter what is the nonlinear term. It doesn't matter what is this thing, what is this thing. The nonlinear contribution cancels out. What's left is just the linear dissipative term. So that's why I get the scheme is unconditionally energy stable. So that's the first nice property. You get unconditional energy state. And you get exactly the same kind of energy dissipation rate. You get exactly the discrete analog of the continuous case. So, and you can do this, as I said, you can do this with third order or fourth order PDF. You still have the same property. You do exactly the same thing. Okay, this is the time discretization. But for this result, this unconditional stability result holds for any consistent Colloquium approximation. Whether you use finite elements, finite difference, or spectral method, as long as your discretization respects the integration by parts. The only thing I need is integration by parts. I don't need anything else. As long as you respect the integration by parts, the full discretization still satisfies the same problem. Okay, so this is about the stability. but I still need efficiency, right? I still need, I have stability, I have accuracy. One more thing I need is accuracy. No, one more thing I need is efficiency. I need to be able to solve this one fast. Okay, how do I solve this fast? This is a couple between phi, mu, and r, right? But r is just a number. So this is just coupled by a number. And if I write this thing as a big matrix system, like this, phi, mu, and r, you see, for the phi mu, I have this constant coefficient operator here. And for the r, I have just a constant in front. And all the nonlinear terms are just depend on the previous time step, just the star, doesn't really matter what it is. So how do I solve this thing? I do a block Gaussian elimination. First to find r, which means I need to solve this once to get r. And once I get r, I solve this equation another times, I get find mu, right? So the total cost of this scheme is to solve this constant coefficient problem, twice. And so now you go back to your simple-minded scheme, IMAX scheme, or whatever, the semi-implicit scheme. So for the semi-implicit scheme, exactly at each time step you need to solve this equation, because you treat all the nonlinear term explicit. So now the new scheme solve this in twice, but you buy what? By doubling the cost, you buy unconditional stability. You buy unconditional stability. So that's the trade-off between this scheme and the semi-implicit scheme. Okay, so that's the scheme. That's the scheme, and so this looks like a very general scheme. It has extremely nice property, accuracy, efficiency, and simplicity. It's all in there, and it looks like magical. But how can this be working for everything? There must be a catch somewhere, right? And the catch is when you do the splitting, you have to do the splitting in the correct way. So the implicit part has to be strong enough to control the explicit part. Right? That's always the case. If you have a time-stepping scheme, if you want to have good stability, your implicit part have to be strong enough to control the explicit part. Otherwise, your numerical solution will be stable. It's never going to blow up no matter what you do, but you get garbage. You can get garbage, stable, but not physical, right? So how do we deal with that if I have a problem which the splitting is not so obvious, and then this is case by case. Right? This you have a free energy, then you have to see how to split this correctly. So I will give you some example. So one very typical example is this free energy again, but now I emphasize that here's a very large coefficient, 1 over epsilon squared, and epsilon is usually the interfacial width. So epsilon is very small, 1 over epsilon becomes very large, and then if you do a splitting, natural splitting like this term will not be able to control this. So if you use this splitting, what happens, you need a time step to be very small to get accurate results. So that's the problem. But you can fix this pretty easy. As I said, this splitting is sort of arbitrary. So what you can do is you can try to extract some positive term from here into the linear part. For example, here you can do S, for example, S is a stabilization constant, take it to be 1. You add some term to the linear term, and of course you have to subtract it from the nonlinear term. So the only thing, now you see, you have this term which will be able to balance this one. So now this term is strong enough to balance this one, but you have to make sure this part is still bounded from below. still boundary flow below. But this you can show, because here, double well potential, for example, has fourth order degree, which will be able to balance this. So this is always true. So if you do this, then you can still get very accurate result with larger time steps. So here some example is without this type of stabilization, you need a very small time step to get a reasonable result. If a time step is large, you get garbage. But if you do this stabilization, even with a large time step, you still get very accurate. So this is one thing. Okay, the second caveat is why. So I said you double the cost by use unconditional stability. So what unconditional stability can give you is if you want to take advantage of this, you need to do adaptive time step. So the unconditional stability means your time step will only be controlled by, only be dictated by the accuracy, not stability. Right? So for gradient flow, this is the typical energy. Right? At the beginning, the energy changes very fast, so that you need a very small time step to follow the dynamics. But later on, it doesn't change very much, and maybe after a long time, the energy start to drop again. But during this time, you can go with very large time steps, right, without sacrifice for the efficiency. But if you don't have unconditional stability, your time step will be controlled by the stability, will be controlled by the smallest time step needed here, not by the accuracy. But if you, with the new scheme and adaptive time stepping, then at the beginning, you have to use small time steps, and later on, your time step gets bigger and bigger. And so here can be something like 500 times bigger than the initial time step, and you still get the same accuracy. Keep the same accuracy. So with those two things in mind, then this becomes very efficient and powerful. I'll mention a little bit about the convergence and error analysis. So we have done the convergence and the error analysis. What I'd like to mention is previous stability and error analysis for semi-implicit schemes. If you want to do if you want to treat a nonlinear term explicitly, and if you want to get some theoretical result, people always assume that the uniform Lipschitz condition, which means you assume the second derivative of f double prime is uniformly bound. So this is called the uniform Lipschitz condition. But this can never be true, even for double well potential. Double well is fourth derivative, is fourth order polynomial. You take the second derivative, it's the second order polynomial. It's unbounded. So all those assumptions are not justified. But that's what you can do if you have a conditional stable scheme. And since we have this unconditional energy stability, we don't need this condition. We don't need this condition. We can first derive the H2 bounds of the solution, and once with the H2 bounds, we can derive the L infinity bonds. And once you have the L infinity bonds, why do they assume this condition? Is because they don't have the L infinity bond of the solution. So once you have that, then everything goes through. And so we have established the convergence and error estimate for the semi-discrete case. And so with the same type of condition as PDE. So with PDE, you have to have assumption. So we have a convergence result based on the same assumption of the PDE. And you can do fully discrete case with finite elements and a fully discrete case with finite difference. So we just did two examples. Of course, with different discretization, the approach are not the same. So you have to develop different technique to actually prove the error estimate. Okay, so this is too complicated, so I'm not going to go through this, but this can be done. And now I will just, depending on how much time I have, I just go over some applications one by one. Okay, the first one is gradient flow of several functions. So in material science, you often consider this type of problem. You have hundreds of different type of material, and you put all them in heating place and try to come up with some new material. And so this process will be dynamically governed by a free energy, by a free energy like this, and this is a linear part, and this is a nonlinear part, and usually you can, this K is a number of components. You can have tens or hundreds of different components, right? And then what you get is a sequence of Canhelia or Alencar type equation coupled together, to the gradient flow associated with this free energy. So it will be a sequence of Canhelia equation coupled together. And so for those sequence of Canhelia equation, you can just introduce one, you just need to introduce one single SAV, and still stick this R divided by itself in front of each of the variational derivative, and you have one actual equation here. And then you can construct a scheme, and here, previous time I did it based on BDF, and here's based on Quaker-Nicholson. You can do any type of scheme, and you can get exactly the same type of property, unconditional energy stable for this scheme. And the key thing is how simple to solve this system. You see, everything is just coupled by this one single number. So you do exactly the same thing. You write it as a big system, and you solve this. You solve this one single number first by Bloch-Gaussian elimination, which requires solve decoupled equation like this for each component. And once you have that, you solve it another times to get all the phi. So the computation cost is still twice as the semi-implicit scheme, but now you have unconditional stability. And so here I've been working with a material scientist. So he's a master of using this type of modeling to simulate material processing. And this one is just some result on grain walls. This is one of the started with random initial condition. This is after 50 iteration and 100 or 200 iteration. You see those grain boundaries develop. So previously, if you use explicit or semi-implicit discretization, you need to use very small time steps to make this work. And now with this unconditional time stability scheme, you can do coupled with adaptive time step, you can do this very fast. So this is a big one advantage when you have multiple components with multiple components. Okay, the second example is molecular beam epitaxial, which is just to develop a thin film growth. So phi, here phi is the thin film height. So you have this kind of energy, free energy, and naturally this is the linear part, and this is a nonlinear part, right? Natural splitting is this. But unfortunately, this part is unbounded. Right? This part is the log of this thing is unbounded. So it's unbounded from below by itself. Even though the whole free energy, you can show it's bounded from below. But this part itself is unbounded from below. So you cannot directly apply the SAV. But I pick up this example. Sometimes you need to do a little bit of work. So here, you just need to, again, borrow some term from the positive, from the linear part. Just take any alpha bigger than 0. You take any alpha bigger than 0, then you can show this part will be bounded from below. And once this part is bounded from below, then you split your energy into this part, linear part, you already subtract a small part, and the rest, so the rest you have this part here. Right? So the rest, but you know this part is bounded. So you define a SAV like this, and then the rest is just routine. So this is a recipe, right? This scheme is just a recipe. You have any free energy, you split, and then the rest is just recipe, no matter what. You do exactly the same.
So is there a trade-off here? So for example, is your time step restriction based on the magnitude of C naught?
It's very almost independent. Almost, I have, for example, you C naught, if it's 10 to the 100, maybe the time step will some restriction. But for C naught, between order 1 to something like 10 to the 5 or 10 to the 6, it's a very little difference.
Because if you throw too much into the nonlinear term, then you get back to the other example, you might have poor accuracy.
Not really, because the C naught is just a constant. It's not like this constant does not affect the two. And so there you can. The rest is just a recipe. So I'm going to not going to bore you with all the details. You have scheme, and you can show unconditional stability. And each time, the main sentence, each time you only need to solve equation with constant coefficient. And in this case, because the energy has bilateral operator, you have to solve force equation with constant. Here are some of the simulation result. I guess the important thing is to see the energy decay, the energy curve with different time step, and the scaling of the energy. So people predict the energy will decay as a log t, and it fits very well. It's computed and fitted with this coefficient log t. So you do see the energy decays logarithmically. Okay, the second example. Okay, third example is problem with constraints. So for many problems, you do not only it's energy decay or energy conserve, but you have other constraints like volume preserving, like mass preserving, and surface area preserving, things like that, right? So those cannot be represented. It's extra condition need to be satisfied. So, for example, we consider the dynamics of the phase field, the vesicle memory model, which is you start with the bending energy. So the vesicle memory, the evolution is governed by this bending energy. It's quite complicated. You have a phi is a phase variable distinguish the inside membrane or outside membrane. And the epsilon is an interfacial width, should be small. And so you have two constraints. Volume should be preserved. So the vesicle membrane, the volume is preserved, and the surface area is also preserved. So the surface area is quite a complicated formula. It's also preserved. So how do you evaluate this while keeping those preserved? So there are two approaches in general. One simple approach is just penalty approach. So what I mean by penalty approach, your volume, this is your initial volume, this is initial surface area, and you make a square, and you multiply by a big constant. Right? You penalize the free energy. So that if you choose your Garmin eta sufficiently small, then this will be approximately preserved. So now you add those two terms in the free energy, then you go back to your machinery. It's automatic, right? You can apply the scheme.
But you be some idea of the
That's right, how to split. So this is the next step.
And how to choose gamma and eta.
Yeah, gamma eta just choose, depends on how accurately you want to do. 10 to the 5, minus 5, 10 to the minus 8, you do things like that. And so you can do this straightforwardly with SAV, but turns out it doesn't work so well if you do this straightforward like this, because there are so many small parameters here. You have gamma, you have eta, and you have another epsilon here, and you treat everything the same way, and it dictates to have a very small time step to get to reasonable accuracy. So this thing doesn't work so well just by doing this with one SAV. So the idea is for each nonlinear term with a small parameter, you introduce one SAV, and here is for the surface area, and here is for the bending energy, the nonlinear part of the bending energy. So you expand the bending energy, the linear part you put it here, and this volume constraint is also linear, so you can combine this volume constraint here. And then the surface area constraint is here, and the bending energy is here. So you introduce two square terms, right? Two SAV. Each SAV control one small parameter, and then you rewrite your L2 gradient flow by using this by using this two new variables U and V. You get this, and then you apply it. So I have two SAV, and then you can write the scheme just like before with in terms of quantum Nicholson. Right. So here's the linear implicit part, and all those stars are the nonlinear part. Stars are the extrapolation. And so this looks very complicated, but in fact, the only thing which couples phi mu uv together is this un plus 1 and vn plus 1, but they're two numbers. They're just two numbers. So now, if you write a big matrix, so you have u and v you need to solve, but u and v can be solved by solving a 2x2 linear system, which you can do it by hand. So u and v are just one scalar variable each. So then the rest is just a semi-implicit scheme, right before. So still very easy to solve, and then you have unconditional energy stability like this with that. And so here are some numerical simulations. And if you don't have if you don't use penalty, of course the volume will grow, and eventually it will settle down. But if you have if you put here we didn't put too small. If you can put small, it doesn't really matter, and you conserve the volume exactly, and here you conserve the surface area. And here are some simulations. You start with 4 vesicles, and without the surface area or volume conservation, everything will merge into a big ball. And but with surface area, if you add the surface area conservation, then it can evolve into very different shape, peanut shape or donut shape. So this you can actually observe in experiments, in biological experiments. Okay, so the next example is an example to couple gradient flow with other physics. Right? If you just to be able to solve gradient flow, you are still limited. But many systems is a gradient flow, but coupled with momentum conservation, mass conservation, coupled with other conservation laws. And here, example is two-phase incompressible flow. Suppose you have oil and water, and you mix them together. And so how to simulate this thing? And we use a phase field approach, where phi represents the two different fluids, the location of two different fluids, and then you have a free energy, just like in the Alan-Kahn and Cahill equation, and then you have your Cahill phase field equation. So this is basically the Cahill equation, except you have a transport term with respect to the fluid velocity. So everything will be transported by the fluid velocity, right? It's you have two fluids. And then you have a momentum equation, and then you have incompressibility. So for the moment, for simplicity, I assume the two have the same density, but it doesn't have to be. We have a model for different density, and the algorithm works the same way for different density. For different density. So this is the phase field model for two-phase incompressible flow. So the coupling is here. Right? Here's the coupling. And so this system is thermodynamically consistent, so that you have energy dissipation. So you still have to be dissipative or conservative. Otherwise, we don't know what is the structure preserved. So this is the type of structure we'd like to preserve. The total energy dissipated. Then, as before, to treat the phase variable, you can introduce SAV to treat the phase variable, and of course you have this is just the Cahill equation like before, except you have an extra convective term here, transport term here, and this U is a velocity. So phi bar is extrapolation. It's extrapolation. U hat. There are two different ways to do it. I can do extrapolation, or I can do implicit. So, or do U hat. So what is U hat? So we have a phi, we have mu, we have a u, we have p. So it's a complex system with a lot of different variables. So my goal is to decouple all the computations. So to treat the momentum equation, the Navier-Stokes equation part, I'm going to use a sort of a projection type scheme. So I'm going to treat my pressure explicitly. So at each time step, I'm going to solve the intermediate velocity u tilde by solving this elliptic equation. So you see here is treated semi-implicitly. So it's not constant coefficient. This is, if you want the unconditional stability, it's not a constant coefficient for the momentum equation anymore. But this term you already computed from the previous term, this step. So this is a sort of just an elliptic equation. And once you get u tilde, you solve a pressure Poisson equation to get P. So this is a projection step. You project onto the, you see I have divergence free condition which I did not ask here. But once you do this, the final velocity will be divergence free, because when you take the divergence, you get the divergence equals to this, which is exactly this equation. So this is a projection time scheme. So you see it's a decoupled scheme with second order accuracy, but you can still prove if you take this thing to be u tilde, there will be weakly coupled, but you get unconditionally stable scheme, and the weakly coupled it's a linear system, it's positive definite. So you can use a simple preconditional, constant coefficient precondition to precondition it. But most of the time, since we are simply going to treat, because that part, that transport part, is not that important. In most two-phase flow, you can treat it explicitly. Once you do that, then everything becomes decoupled. And,
So because of the projection step, you're stuck with a best second order accuracy?
that's right. Yeah.
Okay, so there is a trade-off here with trying to decouple.
That's right. If that's the best you can do with the projection, it's a second. So otherwise, you get a system which is it's a saddle point system. It's a headache to solve. So that is okay. I guess I can still go over this. So all of the previous examples are dissipative systems, but now I give you an example of a conservative system, nonlinear Schrödinger equation. So the nonlinear Schrödinger equation is like this. So f is some nonlinear function, smooth nonlinear function, and it preserves the mass and energy, So for this equation, there are tons of scheme developed, right? For this scheme, so symplective scheme, all kind of scheme which try to preserve mass and preserve energy. But no matter what you do, you cannot come up with a scheme which is linear, second order, and conserve energy. So this, no such scheme exists so far. Linear, second order, and energy conserving, and only involve constant coefficient. So there's no such scheme so far, but we can construct such a scheme by using the SAV reformulation. So you still take, this is by EU, and this is always positive, and then you rewrite your nonlinear Schrödinger equation by sticking the same thing here and write another equation. So since it's complex, the values are complex, you just need to take 3 out. So you do some derivative. This is what you come up with, and then you can discretize this, right? You can discretize those two equations by doing a Quantum-Nicholson. For conservative system, the best to do is Quantum-Nicholson. For dissipative system, it is better to do it with PDF. For dissipative system, if you don't have if you use Quantum-Nicholson, the initial error will never be that. So here you have a second order scheme. Looks awfully complicated, but doesn't really matter. All of those are linear, explicit. So you end up with a linear equation, second order, linear equation, second order, and it's energy conserved. It conserves the energy exactly, just like in the PDE, conserve the energy, but we cannot conserve. We cannot conserve mass. Mass is easier to conserve in most cases, but here we can only conserve energy. We cannot conserve mass. And how to solve this? To solve this is just like previous. You solve R first by solving Laplace equation, and once you solve R, you solve another Laplace equation. So the scheme is should be simple. So one last example, I'm not going to go over this. It's a very interesting example. Now this example, this is not a gradient flow. It's just a Navier-Stokes equation. So how do you apply the SAV method to solve this? And so my colleague Steve Dong come up with some very interesting idea. It probably will take 10 minutes for me to go over this. But the bottom line is the idea can be applied to solve systems which are not gradient flow. Everything else is sort of started with free energy. But Navier-Stokes, we don't start with free energy. It's conservation law. But it still can do it and construct schemes which I've never seen before, which is linear, which is linear and unconditionally stable. For Navier-Stokes equation, before there's no such scheme exists. If you treat your nonlinear term explicitly, it cannot be unconditionally stable. Here, it's linear and unconditionally energy stable. Okay, I will conclude. So the SAV approach enjoys many advantages. You can build a second order very easily, even you can do higher order. And it leads to linear decoupled equation with constant coefficients, even for gradient flow with multiple components. And it can really apply to a very large class of gradient flows. And it can be combined with any gradient type special discrete. And you have rigorous convergence and error analysis to back it up. So the two caveats for applying this thing is one is you have to have a good splitting, and the second is you need to couple it with adaptive time step. Then you can get the most out from the SAV approach. And in fact, they are not restricted to gradient flows. They can do conservative systems, and they can even do things like Navier-Stokes. So very interesting. But there are also some challenges which lie ahead. So one of the challenges is how to deal with highly nonlinear free energy, where you don't really, there's no way you can see how to take out the leading linear part. So some highly anisotropic free energy, then it is a little bit harder to do. So this is one challenge. And for dealing with this, probably we will have ways to introduce extra dissipation term, and then you have extra dissipation. The second thing is how to do numerical scheme, SAV schemes which are bound preserving. Something like you have a density, something like a density which is positive. And currently, this approach, there's no mechanism to do maximum the bound preserving stuff. So we actually have to do it with different type of scheme. So those are the challenges, some of the challenges to apply this. And so if you want to know a little bit more, there are 3 papers. The first one is a very simple notes, just introduce the method. And this one is just accepted in exam review. It's a fairly long paper. So I basically followed the structure of this paper, sort of, with some new materials. And here's a convergence analysis. Okay, I will stop here. Thank you.
Questions?
Sometimes you have like non-usual boundary conditions, like Raban boundary conditions.
That's fine.
Where the energy will have a term that is over the boundary, right?
Yeah.
Will not be
That's
fine.
fine.
And a second question, you mentioned that it can be extended to higher order.
Yeah.
And you said in practice, you haven't proved it yet.
The problem with high order is numerically, you all have unconditional stability up to 6th order. But since we use the energy type of proof, there's no energy type of proof for this. All the proof in ODE, it's sort of the A-type stability proof. You assume your ODE is is very simple. That type of proof doesn't go over here. So, but numerically, it is unconditional stable. We don't have a rigorous theoretical proof, but it's safe to use.
So there's no point anymore using the like convex splitting. Is that
Yeah,
any
for-
benefit to using convex splitting?
For me, I don't see any point in using convex splitting.
Okay. We have refreshments in the can room. Thank you very much. It's a great talk.